This video is brought to you by mywayteaching.com.
In this part, we are solving one more simple problem, that is example 4. Estimate the speed of sound in air at standard temperature and pressure. The mass of 1 mole of air is 29.0 into 10 raised to minus 3 kg. So this is the question they have given. Here we have to find out the speed of sound in air. So let us find the solution for this question. Okay. We know that 1 mole of any gas occupies 22.4 liters at standard temperature and pressure, isn't it? We know this. So, density of air at standard temperature and pressure is given by mass of 1 mole of air by volume of 1 mole of air at STP. So here we know mass of 1 mole of air is 29.0 into 10 raised to minus 3 kg. They have given in the question. And just now we saw the volume, that is 22.4 liters. 22.4 into 10 raised to minus 3 meter cube. So we get 1.29 kg per meter cube. This is the density of air at standard temperature and pressure. Okay. According to Newton's formula for the speed of sound in a medium, we get for the speed of sound in air at STP. So that speed of sound is given by 1.01, that is standard atmospheric pressure, 1.29, that is density, just now we studied, we get 280 meter per second. This is the speed. So the result, whatever we got here, it is about 15% smaller as compared to the experimental value. Because we know that the speed of sound, it is experimentally it is 331 meter per second, but what we got here, it is 280. So it is 15% smaller than the actual experimental result. Then what's wrong here in our calculation? Why that 15% error is coming? See, if we examine the basic assumption made by Newton that the pressure variations in a medium during the propagation of sound are isothermal. That is the assumption made by Newton. Okay. So that based on that assumption, it may vary, but according to Newton, pressure variations in the medium during the propagation of a sound are isothermal. So we find that this is not correct. It was pointed out by Laplace that the pressure variations in the propagation of sound waves are so fast that there is little time for the heat flow to maintain constant temperature. So, before maintaining that constant temperature, there is little time for the heat flow. It is not isothermal as said by the Newton. So, these variations therefore are adiabatic and they are not isothermal. Okay. So, for adiabatic processes, the ideal gas satisfy the relation that is given by PV raised to gamma is equal to constant, and delta PV gamma is equal to 0. If you differentiate that, we get, thus for an ideal gas, adiabatic bulk modulus is given by this is the bulk modulus, isn't it? Where gamma is the ratio of two specific heats, that is nothing but Cp by Cv. We know this, isn't it? And the speed of sound is therefore given by gamma p by rho. This modification of Newton's formula is called as Laplace correction. For air, the value of this gamma is 7 by 5. Now using this Laplace equation to estimate the speed of sound in air at STP, we get an exact value of 331.3 meter per second, which agrees with the measured speed. If you calculate it using the Newton's formula, then there was an error of 15%, but since we got that pressure variation is an adiabatic process, we modify that formula and Laplace correction the new formula, and using that formula, if you calculate the speed of sound in air, we get the correct value which matches with the measured value. Now let us study the principle of superposition of waves. What is this principle of superposition of waves? See what happens when two wave pulses traveling in opposite directions cross each other. If you think one wave it is moving like this and the other one is coming like this, if these two they cross each other, what happens? It turns out that wave pulses continue to retain their identities after they have crossed, which means if it is coming like this and if another wave is coming in the same direction like this, even though they have crossed, They'll maintain the same identity once they have crossed. But when they overlap, the wave pattern is different from either of the pulses. You can see in this particular figure the situation when two pulses of equal and opposite shapes move towards each other. When the pulses overlap, you can see here, when these two pulses, they are moving in opposite direction, when the pulses overlap, what happens? The resultant displacement is the algebraic sum of the displacement due to each pulse. This is known as principle of superposition of waves. According to this principle, each pulse moves as if others are not present. So the constituents of the medium before suffer displacements due to both, and since displacement can be positive or negative, the net displacement is an algebraic sum. So this figure you can see here, it gives the graphs of wave shape at different times. You can see the dramatic effect in figure C, and the displacements due to the two pulses have exactly cancelled each other, and there is zero displacement throughout. See, to put the principle of superposition mathematically, let us consider y1 x comma t and y2 x comma t be the displacement due to two wave disturbances in the medium. If the wave arrive in a region simultaneously and therefore if they overlap, then the net displacement will be algebraic sum of these two, isn't it? That's what we studied before. That net displacement will be the algebraic sum of these two waves. If we have two or more waves moving in the medium, the resultant waveform is the sum of the wave functions of individual waves. That is, if the wave functions of the moving waves, if you consider as y1 is equal to f1 x minus vt and y2 is equal to f2 x minus vt and up to yn, if you consider the wave function describing the disturbance in the medium, we can write it as summation of all these f1 f2 up to fn. We can represent it in the summation form. Sigma I is equal to 1 to n f5 x minus vt, isn't it? So the principle of superposition is basic to the phenomenon of interference. See, for simplicity, you just consider two harmonic traveling waves on a stretched string, both with the same angular frequency omega and same wave number k and therefore the same wavelength lambda. On a string, you just consider two harmonic waves. Their wave speeds will be identical, and we just assume that the amplitudes of both the waves are equal and they are traveling in the opposite direction of x-axis. The waves only differ in their phase, remaining parameters are same. So we'll describe those two by the functions So the first the wave, that is y1 x comma t, is equal to a sine kx minus wt. This is the first one. And the second wave is y2 x comma t, a sine kx minus wt plus pi. So they differ only in phase, and all these parameters, remaining parameters, are equal. So the net displacement is then, by the principle of superposition, we can write it is the algebraic sum of these two waves. So it is equal to y1 x comma t plus y2 x comma t. So y1 is a sine kx minus wt, and y2 is a sine kx minus wt plus pi, isn't it? So this is, if you take a common, we get sine a plus sine b, which is equal to 2 sine a plus b by 2 isn't it, into cos a minus b by 2, and finally we get y of x comma t is equal to 2a cos pi by 2 sine kx minus wt plus pi by 2, isn't it? So this is also a harmonic traveling wave in the positive direction of x-axis with the same frequency and wavelength, but the initial phase angle is pi by 2. The significant thing is that its amplitude is a function of the wave difference pi between the constituent of two waves. That amplitude is 2a cos, yes, pi by 2. For pi is equal to 0, when the waves are in phase, we'll get the equation for pi is equal to 0. In this case, the resultant amplitude is 2a, and for pi is equal to pi, the waves are completely out of phase, and the resultant wave has zero displacement everywhere at all times. This y x comma t is equal to 0, it refers to the complete interference, constructive interference of the two waves when the amplitudes add up in the resultant wave. The equation that we studied now, 2a sine kx when the phase is 0, this is the example of constructive interference, and this is the example of destructive interference when the amplitude subtract out in resultant wave. Okay, you can see this figure, it shows these two cases of interference of waves arising from the principle of superposition, constructive as well as destructives. You can see both examples here in this particular figure. Okay, so this is the example of constructive interference, and this is the example is destructive interference, where amplitude y of x comma t will become 0 here. Here y of x comma t is 2a sine kx minus wt.